Do you ever have a tight deadline when you are working on the material model calibration? You may have already installed MCalibration, the best calibration software available, but you still want to know more about how to speed up the calibration. Specifically, which optimization methods should you use? There are a lot of choices in MCalibration. Today, I will talk to you about the different choices. I will describe what they do and basically go through what option you should use in different scenarios. So let's get started. So for this purpose, I have prepared a test case where we have both tension and compression data. And here are the files. You can see that the data files have 3 columns: time, true strain, and true stress. One is tension, one is in compression. And in a real situation, you may have more data than that, but let's just use this for our example today. So I selected both files here. I'm going to click on copy. Then I'm going to go to a window of MCalibration here, and I'm going to paste in these 2 experimental files. So I'm going to go to Edit, Paste, and here they are. So tension and compression. And to make this concrete and like a nice little example to work through, I will pick a material model, and I will pick, in this case, the 3-network model as part of the PolyU model library. So I'm selecting the 3-network model here, and I say OK. And here's the initial set of parameters that MCalibration picks for you. So if you click Run once at this point, we'll see that the predictions are OK, but they're certainly not that great. There's particularly large strains here. There's a big difference. The average error, the NMAD fitness is the average error of the prediction at this point with these parameters, is 32%. So it's not all that great. I will click on calibrated models and lock. I will lock this initial guess here, and you will see that in a little bit why I did that. So I'm locking this one here. I'm going to optimization progress. And what I really want to focus on today is, okay, so if I run calibration, there are a number of choices here. Which of these choices should you do in different scenarios, and why? So that's really what I want to focus on. I will start here with a very simple one. I'm going to do quick automatic method. So this is not something I typically do, except for demonstration purposes. So I'll pick that here. I'm selecting 8 CPUs. What that means is that the software will use up to 8 CPUs, depending on what you're trying to do. In this particular case, there are only 2 experimental files, 2 load cases available. So the software will actually only use 2 CPUs for this calculation. I have unlimited time for the calibration. I allow the software to work as long as it likes, but I did stop it after 30,000 function evaluations. It's a very large number, but I let it to have a hard end inside there. I also turned off the save calibration during the optimization. It doesn't really matter for what we're doing here. So if I click OK, you will see that it starts to manipulate these numbers using that particular optimization method. So let's just let this finish the calibration, and I'll be back in a few seconds. And after about 3 minutes and 4 seconds in this case, the calibration finished. And you can see that the calibrated predictions are actually pretty good. The error started out at around 32%, and now it's down to 10%. So it's a substantial improvement in the predicted model predictions here. So these are the final parameters that they came up with. And it used 410 function evaluations to reach this point. So this is pretty good, and if you have about 2-3 minutes to do a calibration, this method is pretty good. It stops by itself very quickly, and that's what it's useful for. If we want to compare different optimization methods, it's useful to look at how the fitness value changes with the number of function evaluations. We can compare it with fitness value versus runtime too, but I think it's easier to just look at function evaluations here. So there is a feature that is handy for this. I'm going to right-click in this graph here. I can save the data that's plotted here to a file. So I was going to call this results, and this was quick optimization. So I'm just going to call it that. And if we go back to where we were, this is the file that was generated for us. So it has the after 20 function evaluations, this was the fitness value. So we can plot this and evaluate different methods using this approach. So that's what I will do. Let's go back and look at the method that we used. So we used the quick automatic method. And this method is interesting, and it's using actually a few different other methods first. It starts with random search. And so that's what's important to remember, that if you run this optimization method from the same starting point another time, you will get a different result because there's some randomness to this method, this quick automatic method. So that's useful when you try to evaluate the importance of different starting points for a calibration. So what about these other choices here? There's a relatively long list. How does these other methods work? I typically recommend the extensive automatic method, and there are a few different options here. With this one, you can have include a random search or not, you can include these methods or not, and you can also click this one, repeat the optimization until no further improvements. They make it run longer, so basically run it one time, and then it starts over again, and then that can give you sometimes better results. So that's what I want to explore here, these different choices for the material model calibration, what methods they're available, and then how do they really work. So the way I performed this study was I go back here, I did this, I exported the data, then I go to calibrated model. Since I locked this one, as you remember, I can select this row and I can copy this model to the table. So what I've done here is I replaced the parameters we optimized with the original value. So I run once, we're back to a fitness of 32 again. And I can run it again using a different methods or the same method to see how the results change as I run it over and over again. And that will allow us to more systematically and scientifically examine the performance of these optimization methods for this very specific problem of this experimental data with this material model. So I did all of those steps, and I'm going to show you some of the results. So let's take a look here. So here's a table that summarizes the results. It's kind of interesting. I was a little surprised when I did this, what came out of it. So here are a case where I allowed MCalibration to only take 100 function evaluations, and then it was forced to stop. And I tried a number of different optimization methods here, as you can see. The quick automatic one is the one we just demonstrated live. And I got these fitness values, and I ran it 5 times in a row. And these are the values I got the 5 times I ran it. And this is the average of them. And then I plotted that down here. Average errors was 22% for the quick automatic method. Okay, so that's actually not very good. I would not use that method, as we will see. The other method that's very interesting is the Nelder-Mead. This is the simplex method. I'm actually a big fan of this one typically. So let me demonstrate what you do here. So this is the slow, careful optimization. It picks the simplex method. And you can specify the min and the max number of iterations. And you can also tell it to either loop or not loop. So what it does is that it runs up to 5 iterations now. And then it increases, it starts over again with a maximum of 6, and then 7, and so forth. So it restarts the procedure when you do it that way. So here I set the minimum to be 5 and the maximum to be 50, and I ran that. What's interesting and important to remember is that the simplex method doesn't have any randomness to it. So if I run it one time or many times, I always get the same results if I have the same starting point. And in this case, with these settings, the error was 27%. So it only went down from 32 to 27 in error. So that's not very good. Clearly one of the worst here in this example. Similarly, if I switch back to the simplex method here, and I, instead of having 5 to 50, I make this 5,000 and this value 5,000. What happens then is you get exactly the same results, because I let the software only take up to 100 function evaluations, so it never reached this point. So these two will give the same results. This one, I was actually surprised how this optimization method worked. It's the best for a very small number of function evaluations. If each function evaluation is very slow, so say in this case we used the 3-network model as the material model, but if you have a more complicated material model that requires MCalibration to call an FE solver, Abacus, ANSYS, Alice Dyna, or something like that, then the calculations for each evaluation of parameters will be much slower. So you may not be able to run that many function evaluations because it costs too much, it takes too long. In a situation like that, I think that this optimization method is actually the best. I didn't remember that, I didn't realize that. So this is the Powell method, an unconstrained optimization method. And I usually don't change the trust region or the trust radius values there. They are usually good enough the way they are. But if you run that, it converges very quickly. It's an excellent model for have rapid convergence from a starting point. And that is my preference for that. The optimization method that I typically recommend, extensive automatic, had an average error that was twice as large, but it's still pretty good after 100 function evaluations. It takes a little longer for it to start up. And in this case, the automatic method with repeats, that is, when you activate this flag, gives you exactly the same results. And the reason for that is we only allowed 100 function evaluations, so it never get a chance to restart. And the CMAES method, just to show that one, is this one, is a covariance matrix adoption evolution strategy kind of method. It doesn't work that well when you have a small number of function evaluations. It takes a longer time for that to get calibrated and get going. So if you have only up to about 100 function evaluations, I would pick the new UOA method as the procedure to use. But if you change, we say we allow ourselves up to 500 function evaluations, and then we stop, then the situation becomes a little bit different. The quick method usually is about the same between, it gets a little better, but it stops so quickly. So that's not a good one if you can allow up to 500 function evaluations. If you look at the numbers here, you see that the two best ones are the extensive automatic, which is what I usually use, or the new UOA method. Those are very similar here in terms of the averages when you restart them. And the error here is 5%. It's actually pretty good calibration at this point for 500 function evaluations. Now, if we switch over to allow the software to take 5,000 function evaluations, it's not that often perhaps you do that, but you will see that the results change a lot. It's kind of interesting. You see here, if you let it to do 5,000 function evaluations, the Nelder-Mead simplex method gets better, down to 7% error. It's not all that good or bad. It's kind of like, okay, that's not too bad. The thing about the new UOA method is that it doesn't really improve after about, in this case, 500 to 1,000 function evaluations. It doesn't improve for a long time. So it gives a very quick calibration, and then it kind of flattens and stops. The automatic extensive method does improve, but not as much as the repeat. If you really, really want good results, and you're willing to wait and do more function evaluations, the two choices that I recommend is the extensive automatic with repeat, so you restart it many times, or in fact the CMES method is the most perhaps best for many function evaluations. As you can see here, the average results are better for that than the automatic repeated one here. Another way to plot this data that I think is kind of interesting is to plot these traces of optimization progress. So I did that for a few different methods here. So this is kind of an interesting graph, fitness value versus function evaluations. And I'll see some of these curves are so far close to the origin. So 100 function evaluations is really far in here. Then I'll let some of these methods run for a very long time to see how the convergence, the error keeps going down. And it's a little hard to see here. So I plotted this in a different way. Since plotting all the data, I zoomed in a little bit. So this is the same x-axis, but a little bit closer to on the y-axis. This purple line here is the automatic extensive under repeat. And this one is an interesting one. This particular calibration did not look very good, and then it really improved here, and it became the best one in the end. It's the only one of all these that I ran that got an error that was less than 3% in the end. But other times when I ran the automatic extensive, I got errors that were about 5%, 4.5, 4, 3. So it's a little bit more of a scatter here, depending on the randomness and stochastic nature of the calibration. We got one. I got one Nelder Mead with a large number on the loop to go close to 3%. Very good too. Then the CMAES method that I said is really good. It is very good. It's very reliable. You get very good numbers between always basically less than 4% here. And that's certainly something that's very useful, because you don't want to run this over and over again. You want to pick the right method for what you're trying to do. And if you zoom in really at the origin, you will see like this is the first 200 function evaluations and the fitness value. See that the red one here is the best. You want to be the lowest fitness value as quick as possible. And that's the new UA method. It really goes down very quickly, but then it plateaus and doesn't converge as much more. And the automatic method that I mentioned has the new UA in it. So it starts with that, then it switches over to the Nelder Mead. So there's a little bit of an interesting sort of evolution of that particular method. So to summarize, if you have a simulation or a calibration that is slow, every function evaluation takes a long time, or you can't really spend more than a few minutes for the calibration, you have really two choices. Either it's the automatic extensive, and that's the one I would use perhaps, or the new UA, which is probably slightly better actually in the most situations when you have a very small number of function evaluations that you need to do. But if you have the time to run many function evaluations, just like I did here, each of these calibrations takes half an hour or something like that. They're pretty quick, relatively speaking. But if you're allowed to do that, if you have the time, then I would switch over to, I would turn on if I go to the extensive automatic, I would turn on the repeat, because that improves the results. It takes longer to run, but it certainly improves the results. Or you can switch over to the new one here. This one, I didn't see it for a second. This one, the CMAES method. It's very robust because it basically uses it's a population of guesses so that it generates from the initial guess, and therefore it is better at not getting stuck at the local minimum, which is the problem with many of the other algorithms. This has this ability to avoid minima a little bit better than the other ones, but that makes it a little bit slower too. It uses more function evaluations because it needs to propagate a whole family of optional solutions as it moves along. So it's an expensive method to use, but it's very robust in its accuracy in the end. So those are my advice for you if you're interested in speeding up these calibrations and getting the best results possible depending on what situation you're in. I hope this was useful, and let me know if you have any questions. Thanks.